Today we're going to begin our exploration of what is known as eigenvalues, which are often viewed as one of the more important tools in the realm of linear algebra. So what we're going to do is we're going to begin by considering a special type of matrix equation, in particular one of the form ax is equal to lambda x. So in this context, we're going to be viewing A as a linear transformation from Rn to Rm, x a particular vector in the vector space Rm, and lambda just some complex scalar generally speaking. Now, although Ax is equal to lambda x is talking about Rn, you could view A as an arbitrary homomorphism and X just belonging to an arbitrary vector space. There's no requirements that A be a numerical matrix in the Rn sense, all right? So what exactly does this particular equation represent? So if you're familiar with fixed points are vectors in some sense x, such that when you apply some transformation A to that particular vector, you get that particular back again. So if we look at this particular equation, ax is equal to lambda x, then x is a fixed point if and only if ax is equal to x, which of course implies that lambda is equal to 1. But this ax is equal to lambda x generally looks at scaled vectors of x, right? Because if we look at the equation ax is equal to lambda x, we're just making x a little bit longer, a little bit shorter, or possibly even changing the direction. But we're not rotating that particular vector. That's pretty much what this little lambda number is and what x is if it satisfies this particular equation. So let's algebraically play around with this equation and see if we can come across something to maybe find all values lambda or vectors x that sort of satisfy this particular fixed point scaled vector equation. So if ax is equal to lambda x and we subtract lambda x from both sides, then we have ax minus lambda x must be equal to 0, where 0 should be the 0 vector belonging to Rn, and if A is an arbitrary homomorphism, that 0 vector should be belonging to the range of the transformation A. All right, so if that is the case, notice that we have a common vector x in the right-hand side of each of these terms, so we can factor out x from the right-hand side. Once we do that, notice that we're going to have a minus lambda I times x is equal to the 0 vector. And keep in mind that I is the identity matrix, so I is the n by m identity matrix, and that needs to be there, else this term does not really make any sense because A is a matrix, lambda is a number, and you can't do a matrix minus a scalar, right? That's not going to make any sense, but you can do a square matrix minus a square matrix, and that's just the scaled version of the identity matrix. So this equation should look very familiar to you if you have studied null spaces of vector spaces. So is there any solution x that makes this true for any a minus lambda I? You should be able to at least give me one of them. So you should be able to prove that x equals 0 is a solution to this equation for all a and lambda. Now, if I just look at the set for which all vectors x belong to, then where does x particularly live, right? So you should be able to see that generally speaking, x is going to be belonging to the null space of the matrix A minus lambda I. And if you don't know what the null space of a matrix is, or the null space of a homomorphism, definitely check that out in our vector space discussion, right? So if A minus lambda I is an invertible matrix, then x equals 0 is the only solution. Therefore, we can of course conclude that the dimension of the null space of the matrix A minus lambda I is going to be equal to 0 if and only if the determinant of this matrix A minus lambda I is not equal to 0, right? i.e. if and only if A minus lambda I is invertible, i.e. non-singular. So with this insight, and in particular this determinant says a lot about the existence of these vectors x and these corresponding numbers lambda, for which this transformation A actually has these 0 or scalable vectors under this transformation. So with that in mind, let's give us this next definition. So if A is a square n by n matrix, and lambda is some scalar, then the determinant of the matrix, A minus lambda I, is going to be denoted by P subscript A of lambda, and this is known as the characteristic polynomial of A. Characteristic polynomial of A. Now, why do we call it the characteristic polynomial of A? Well, characteristic, of course, is just an adjective to distinguish it from polynomials, at least not from the linguistic sense. But why do we call it a polynomial? So if we look at the matrix A minus lambda I, what exactly does this matrix look like? So remember, I is a diagonal matrix, one down its diagonal, so lambda I is just another diagonal matrix with lambda down its diagonal and zeros elsewhere. So A minus lambda I is just going to be subtracting lambda from each of the diagonal elements of A. So if we looked at that in expanded form, we're going to have, for example, A11 minus lambda, A22 minus lambda, all the way down to ANN minus lambda on the diagonal entries, and then we're going to have our AIJs and our AJIs sort of floating around this diagonal entry, and they're not going to be changing. Right? So if we look at the determinant of this matrix, if we, for example, expand across any row or any column, then we're actually going to be getting a polynomial with respect to the variable lambda, where these AJKs are a bunch of our coefficients. So let's actually look at a couple examples on how to construct the characteristic polynomial for a variety of type of matrices. So let's look at the very special matrix A11, A22, A33, with zeros elsewhere, so nice diagonal matrix. And let's look at the matrix A minus lambda I. So A minus lambda I is going to be equal to A11 minus lambda, 0, 0, A22 minus lambda, 0, 0, and then A33 minus lambda, 0, 0. So if I want to take the determinant of this matrix, we've already proven that a determinant of a diagonal matrix is just the product of the diagonal entries. So that's going to be equal to, by definition, the characteristic polynomial of matrix A, and by definition, or results from determinants, we know that it's going to be equal to A11 minus lambda times A22 minus lambda, and then A33 minus lambda, and you can expand that, and you're going to get a degree 3 polynomial, in particular one of the form minus lambda cubed plus some number lambda squared plus some number lambda plus some constant at the very end. And you can figure what those constants are in terms of A11, A22, and A33 for either specific cases or the general case in case you are interested in. Let's look at a particular numerical matrix, a nice little 2 by 2. So for example, let B be equal to minus 3, 5, 2, and minus 1. And let's see if we can find the characteristic polynomial for B. So by definition, the characteristic polynomial for B is going to be equal to the determinant of the matrix B minus lambda I. So that's going to be equal to the determinant of the 2 by 2 matrix minus 3 minus lambda, minus 1 minus lambda on the diagonals, and 5, 2 elsewhere. So by properties of determinants, that's going to be equal to minus 3 minus lambda times minus 1 minus lambda minus 2 times 5. Let's expand this polynomial out a bit by doing some distribution. So that's going to be equal to 3 plus 3 lambda plus 1 lambda plus lambda squared minus 10. And that's going to be equal to lambda squared plus 4 lambda minus 7. That means this is the expanded characteristic polynomial of that matrix B that I mentioned before. Let's define another term to add to the list, and this is going to be very, very important. So this number, lambda, is called an eigenvalue of the matrix A if the characteristic polynomial evaluated that particular number lambda is equal to 0. So if we have, for example, our diagonal matrix A, which keep in mind was equal to A11 minus lambda, A22 minus lambda, A33 minus lambda, and 0 elsewhere, then the characteristic polynomial of this matrix A was equal to A11 minus lambda times A22 minus lambda and A33 minus lambda. Now let's assume that we want to find the eigenvalues of A. So we would set this characteristic polynomial equal to 0 and solve that polynomial equation. So if you want to solve a polynomial equation, the goal is, at least the end goal, is to have that polynomial completely factored into linear factors. Because if the product of these three terms is equal to 0, then we can set each of these terms equal to 0 and we can find the solutions. For example, from the first term we have that lambda is equal to A11. The second term is going to give us lambda is equal to A22, and this third term is going to give us lambda is equal to A33. Therefore, this matrix A has three eigenvalues, A11, A22, and A33, which are just the diagonal entries of A. Right, so that would be A, and A minus lambda would be the minus lambdas across the diagonal. Now, let's take a look at that other example that I gave, right? So let's look at the matrix B, which was minus 3, 5, 2, and minus 1. So we've already shown that the characteristic polynomial for B was equal to lambda squared plus 4 lambda minus 7. So if we desire to find the eigenvalues of B, that means we need to solve the algebraic equation lambda squared plus 4 lambda minus 7 is equal to 0. Now, if you don't know how to factor this, that's perfectly okay, but it is a quadratic equation, so you should be able to use the quadratic formula in order to find those eigenvalues. So if we go ahead and do that, we have that lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, right? That's the quadratic formula. So that's going to be equal to negative 4 plus or minus the square root of 16 minus 4 times 1 times minus 7, that's going to be positive 28 all over 2. So we have that the eigenvalues are lambda is equal to negative 4 plus or minus the square root of 44 over 2, and we can actually simplify this, so let's go ahead and do that. So negative 4 plus or minus the square root of 4 times 11 all over 2, which is negative 4 plus or minus 2 square root of 11 all over 2, which is negative 2 plus or minus the square root of 11. So that's going to give us two eigenvalues. The first eigenvalue is going to be equal to negative 2 minus the square root of 11. And the second eigenvalue is going to be negative 2 plus the square root of 11. And those are the eigenvalues for that particular matrix B. So just a quick couple of notes that you should know. So let's assume that A maps Rn to R, i.e. A has real valued coefficients. Then the values lambda that satisfy this particular equation from the fundamental theorem of algebra from precalculus, lambda can be a complex number. Right? So even if your polynomial has real coefficients, it's possible that these lambdas are complex numbers, so do not be scared of that. But if you do remember something from precalculus, if you have a real valued polynomial, if you find one complex eigenvalue, the conjugate of that eigenvalue will also be an eigenvalue as well. So that's a nice little property. Now another theorem that I leave for you to prove is that if A transpose is equal to A, i.e. A is a symmetric matrix, then the eigenvalues of A are always going to be real. Now this is a very, very beautiful property that we're actually going to take advantage of a little bit later. Let's look at another example just for fun and excitement. Let's look at the rotation matrix by some angle theta in R2 to R2, which, keep in mind, was cosine theta, sine theta, minus sine theta, cosine theta. So the characteristic polynomial of R theta is going to be equal to the determinant of the matrix cosine theta minus lambda, cosine theta minus lambda, minus sine theta, sine theta. 2 by 2 matrix, so the determinant's very, very easy to get. So it's going to be equal to cosine theta minus lambda times itself, minus sine theta times minus sine theta, that's going to be positive sine squared theta. Let's expand that out. So it's going to come out to cosine squared theta minus 2 lambda cosine theta plus lambda squared plus sine squared theta. So if we rearrange this, let's put our lambda squared first. So we're going to have lambda squared minus 2 lambda cosine theta, and then we have sine squared plus cosine squared. We should know from pre-calculus that that's just equal to 1. So therefore the characteristic polynomial for any rotation matrix in R2 is going to have this structure. Right? So let's assume that we want to find the eigenvalues of this arbitrary rotation matrix, i.e. we're going to set this equation equal to 0 and solve for lambda. So this is a quadratic equation again, so lambda is equal to negative b, so 2 cosine theta, plus or minus the square root of b squared minus 4ac all over 2a. Right? So we can simplify this just as before, and you can find that lambda is just going to be equal to cosine of theta plus or minus the square root of cosine squared theta minus 1. And you can rewrite this discriminant underneath the radical using some other identities. If you know it, you can, for example, rewrite this as cosine theta plus or minus the square root of minus sine squared theta, if that makes you feel any better. But nonetheless, if sine squared is a positive number, which it typically is, then that's going to result in a complex number. So for example, if theta is equal to 90 degrees or pi over 2 radians, then the eigenvalues of this rotation matrix, so a 90-degree rotation counterclockwise, is going to be equal to cosine pi over 2 plus or minus the square root of minus sine pi over 2 the quantity squared. So we know that the sine of 90 degrees is going to be equal to 1. So we're going to have that lambda is going to be equal to cosine pi over 2. That's going to be equal to 0, plus or minus the square root of minus 1 squared. So that's going to be equal to plus or minus the square root of minus 1, which is going to be equal to plus or minus the imaginary unit I. Right? So notice that we have a real valued 2 by 2 matrix, but both of the eigenvalues are complex numbers, and in particular they are conjugates of each other, right? Because lambda 1 is equal to 0 plus I, and lambda 2 is equal to 0 minus I. All right, so those are our two eigenvalues for this particular rotation matrix. I want to mention a couple identities that are going to be very, very useful later, and they're called Euler identities. So the first one is e to the I theta can be proven to be equal to cosine theta plus I sine theta. So the complex exponential in some sense is a periodic function, and from this, if you take this as fact, e to the minus I theta, you should be able to prove is cosine theta minus I sine theta. So those are two very important identities, and in case you're curious, you can actually prove some interesting identities in terms of sine and cosine. So you should be able to prove, for example, that cosine theta is equal to e to the I theta plus e to the minus I theta all over 2, and sine theta is equal to e to the I theta minus e to the minus I theta all over 2I. So sine and cosine are actually exponential functions, just like exponential functions are the sum of trigonometric functions in the complex plane. We're not going to use these results here, but I just want to mention it since we're talking about complex numbers, because once we get to differential equations later, this is actually going to become very, very useful for interpreting the solutions of those equations. Let's just do one other quick thing. For example, let's look at the matrix A, which is equal to 2 1, minus 1, 3, just to make sure you know how to find eigenvalues, because this is a very important tool. You may want to pause the video and see if you can find the eigenvalues of this. You should be able to at least show that the characteristic polynomial for this is going to be equal to 2 minus lambda, 3 minus lambda, minus negative 1 times 1 is going to be positive 1. So that's going to be equal to lambda squared minus 5 lambda plus 7. So since that's our characteristic polynomial, we're going to have that lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So 7 times 4, we know that's going to be equal to 28. So we have that 5 plus or minus the square root of negative 3 all over 2, or 5 plus or minus the square root of 3i all over 2 are our two eigenvalues, both complex and they're conjugates of each other, right? So that's how you can find the characteristic polynomial and the eigenvalues of a square matrix. Now, one thing I want to do, and it might not seem obvious why I would even want to do this, is everywhere in this particular characteristic polynomial, I'm going to put this matrix A that I am working with for the characteristic polynomial and eigenvalues, and substitute A everywhere I see lambda. And when I see this little constant at the right-hand side, I'm going to put the identity matrix next to it. So let's see what's going on there and what the consequences are. So the characteristic polynomial for this matrix A was found to be lambda squared minus 5 lambda plus 7. And what I'm going to do is I'm going to consider the statement PA of A, which is equal to A squared minus 5A plus 7 times the 2 by 2 identity matrix. Because if you don't have the identity matrix there, you're going to have a matrix minus a matrix plus a scalar, which again doesn't make sense, but that's a matrix. Now this is perfectly okay. So PA of A should be a matrix. So let's see if there's anything special about that matrix. So we're going to be doing 2, 1, minus 1, 3 squared minus 5, 2, 1, minus 1, 3 plus 7 times 1, 0, 0, 1. So let's expand this out. So if you multiply 2, 1, minus 1, 3 by itself, you should get the matrix 3, 5, minus 5, 8, right? So we get that weird looking matrix. And then we're going to have minus 10, 5, minus 5, 15, plus 7, 0, 0, 7. And if you take time and actually add all of those together, you get the matrix 0, 0, 0, and 0, the zero matrix. Isn't that strange, right? Now, is this by chance all of them are equal to 0? You could say that, but if you try another matrix, you'll actually see that this always is true. So the theorem that proves this, which we're not going to go into here, is known as the Cayley Hamilton theorem. So the Cayley Hamilton theorem says this: let PA lambda be the characteristic polynomial of the matrix A, where PA lambda can be represented in expanded form k is equal to 0 to n of akx lambda to the power of k, where these ak are the real valued scalars from that expansion. And now what we're going to do is we're going to define PAA to be equal to the sum from k is equal to 0 to m of the same scalars and then AK, where a to the 0 will be the n by m identity matrix. Then for all a, and then for all a that maps Rn to Rn, then we have that PA of A is equal to the n by n zero matrix. Always true. So here's a very important question. So what? Yeah, it might be a little bit interesting, but what's the actual point to this theorem, and what can you sort of achieve from this? So let's look at a couple things. So example 1, let's consider the matrix A, which is equal to 2, 1, minus 1, 3, for which we've already decided that the characteristic polynomial is going to be lambda squared minus 5 lambda plus 7. So, by the Cayley Hamilton theorem, we have that a squared minus 5a plus 7i must be equal to 0. What I'm going to do is I'm going to solve for this identity matrix term, and that's going to give us minus 7 times the identity matrix is going to be equal to a squared minus 5a. So if that's the case, then we're going to have that I is going to be equal to 1/7 times minus a squared minus, actually plus 5a. And notice that this term is going to have a's in it everywhere because the only term that does not have a is the identity matrix. So what I'm going to do is I'm going to factor out that a out. So I'm going to have I is equal to a times 1/7 times minus a plus 5. Right? So notice that I have a times a matrix is equal to the identity, and I could have factored this out on the right-hand side, and I would get the same exact statement, just reversed. So what is so special about this matrix? That would be the inverse of A, right? Now notice I haven't mentioned that A is invertible, but you should be able to check that the determinant is non-zero. So A inverse, by this logic, is going to be equal to 1/7 times minus A plus 5i, which is going to be equal to, once you do minus A plus 5i, you're going to have 3 minus 1, 1, 2, which is indeed the inverse of that 2 by 2 matrix that I stated before. Right? So let's look at another example just to convince you. Let's look at the matrix B, which is going to be minus 3, 2, 1, 2, 1, 2, and 1, 0, and 4. So I can ask you, what is the inverse of B? So if that is the case, you should be able to find the characteristic polynomial of the square matrix. Every square matrix has one. So that's going to be equal to minus lambda cubed plus 2 lambda squared plus 16 lambda minus 25. Now, the first important theorem that Cayley Hamilton actually represents, this number is negative 1 to the power of n times the determinant of the matrix A. So since A, or in this case B, is a 3 by 3 matrix, then the determinant of that matrix B is going to be equal to the opposite of that constant, which is going to be equal to 25. So as long as there is a non-zero constant here, that means the inverse that this is the characteristic polynomial of is invertible. So we can find that, right? And if you sort of think about that logically by the Cayley Hamilton theorem, that means this statement, PBB, is going to be equal to minus b cubed plus 2b squared plus 16b minus 25i. And what do? We solve for that identity matrix, but if there was not a constant there, you couldn't do it, i.e. you can't find the inverse because in that case it wouldn't exist. So if that's the case, let's sort of go through that motion and see what we get. So we're going to have, by the Cayley Hamilton theorem, that the identity matrix is going to be equal to, once we factor out that b, we're going to have 1 divided by 25 times minus b squared plus 2b plus 16 times the identity matrix. So since we have b on the left-hand side and we could do it for the right, that means this term can be found to be the inverse of b. So as long as you square that matrix b, then negate it, then add the scalar multiple of 2 to each of them, add the 16 identity matrix, add them together, that will give you the inverse matrix once you divide by 25. So therefore, the inverse matrix can be found once you work out the calculations to be 1 over 25 times minus 4, 8 minus 3, 6, 13 minus 8, 1 minus 2, and 7, where this number in the bottom is the determinant of b. right? So that's one of the very important consequences of the Cayley Hamilton theorem, i.e. you can quickly find the determinant and also find the inverse of the matrix without having to do, for example, Gauss-Jordan elimination or some other method like the Cramer's rule or whatever, right? So those are some of the basics associated to eigenvalues, in particular how they result from the characteristic polynomial and sort of how they result to fixed points and scaled point of a particular homomorphism, but there are so many more properties that are left to discuss, but we'll talk about them in the next video. But until then, take care. Thank you.